Okay, in this video right here, we're going to be looking at doing electrophilic aromatic substitution when we already have something on the benzene ring. First, let's look at monosubstituted derivatives. The substituent that we have on the ring originally is going to affect the electrophilic aromatic substitution in two ways. And the first way is how reactive is the compound relative to benzene. Okay? So, if we have an electron donating group on the benzene ring, we're going to call this ring activated. Okay? And this means that the compound that results is actually more reactive in electrophilic aromatic substitution than is benzene. Good examples of electron donating groups include the strong electron donators, OH, NH2, and alkyl derivatives of amines. Moderate electron donating groups are OMe and acylated amines, and weak electron donating groups are the most common ones that we see of this class are alkyl groups. Okay. The other type of substituent is called an electron withdrawing group. An electron withdrawing group results in a ring that is deactivated relative to benzene. Okay. So anything with an EWG on the benzene ring is less reactive than benzene is in electrophilic aromatic substitution reactions. Okay? Good examples of electron withdrawing groups are here. Strongly electron withdrawing groups are protonated amines, nitro groups, and cyanides or nitriles. Moderately good EWGs are anything with a C double bond O, a CF3, or a sulfonate, and halogenated benzene rings are weakly electron donating, or weakly deactivated. Okay? Alright, so this is the one effect that you see with groups. The other effect is on their orientation. Where do the new substituents go when you perform an electrophilic aromatic substitution on a benzene ring that already has something on it? We can summarize the rules of direction in three phrases here. Situation number one, all electron withdrawing groups are ortho paradirectors. Situation number two, all electron withdrawing groups except halogens are metadirectors. And situation number three, halogens are ortho paradirectors. What do we mean by directors? Well, what we mean is to what position on the benzene ring do these substituents direct new groups through electrophilic aromatic substitution reactions? Okay, so let's take the first case here. This is anisole right here. This is moderately activated ring, and what we find here is that if you did any electrophilic aromatic substitution, I've used chlorination here as an example, you will get predominantly the ortho para products. Okay? Very little of the meta. Usually more para than ortho due to steric reasons, but still significant amounts of both. Okay, this deactivated ring here contains the electron withdrawing group nitro, and an attempt to sulfonate this ring would result in almost exclusively the meta sulfonic acid, as shown here. The halogenated benzene ring, shown here, undergoes electrophilic aromatic substitution primarily at the ortho and para position. So in this Friedel-Crafts acylation reaction shown here, you would expect to see mostly the ortho and para products, and again, more para than ortho in most cases. Okay, so in these next few slides, I'd like to address the reasons for ortho-para direction. And what we're going to do is we're going to look at anisole nitrobenzene and chlorobenzene and just see what the effects of electrophilic attack at various positions are. Okay, so the first case we'll look at ortho attack on anisole to and we'll use the bromination reaction as the example reaction. Okay, so the electrophilic attack, as shown right here, initially produces the compound that has a carbocation right here, right beside the electron donating group, which is usually a pretty good situation, and you can draw two additional resonance structures due to the allylic nature of this carbocation. And we find, however, that one of these resonance structures is particularly good. That's this one, okay, right here, because this one arises from the lone pair donating to the carbocation, and this resonance structure has an octet at every atom. So this is probably the only one that you can say that for, okay? So attack at the ortho position leads to a really nice resonance form shown here. Attack at the meta position, what we find here is that when we draw the standard allylic resonance structures for carbocations, is that we totally bypass the methoxy group. In no case is the positive charge ever right here at this position. It completely bypasses that in all the resonance forms. So when you attack the meta position, you don't get this excellent stabilization of the carbocation that you get when you attack the ortho position. What about the para position? Okay, and I apologize, this extra arrow is here in every one of them. But when you attack the para position, it's kind of like the ortho position. You'd still draw three resonance structures that you draw for any type of allylic carbocation, or this is a doubly allylic carbocation. But notice right here, we have the carbocation, and it's right beside the electron donating group, the methoxy group, and it's the lone pair donation that leads to this very stable resonance structure that has an octet for all the atoms. Okay, let's look at a deactivated benzene system and look at why it prefers meta. Okay, here is the initially formed resonance form. We have the standard allylic resonance forms that you have when you draw the resonance forms in these doubly allylic systems. And what you'll notice is that when you attack the meta position, never is the carbocation right beside the electron withdrawing group. Recall that when we attack the meta position, it was never beside the electron donating group. Electron donating groups, however, stabilize carbocations. Electron withdrawing groups would destabilize the carbocation. So it's good to never put the positive charge right beside the nitro group. Okay. What about when we attack the para position? Well, here in this resonance form here, you see that you have the positive charge directly beside the nitro group. And that's not a good situation. Remember that the nitro group is really this charged or zwitterionic structure shown here. And the net result here is that you have two positive charges beside each other, and that's a very destabilizing interaction. So we don't want to attack the para position, because that would put the positive charge right where the electron withdrawing group is. Okay, recall that the ortho and para sort of put the carbocations in roughly the same places, and this would also be a problem if you attacked the ortho position. Okay, you would have one of the resonance forms that had a positive charge right beside the nitro group. Okay, what about halogens? Okay, again, it seems like I've just copied this thing right here over and over. Sorry about that. Okay, when we attack the para position, we get the group right here. Normally, we would think that chlorine's electronegative, and thus it would not be a good idea to put the positive charge right beside the chlorine. However, we can do a resonance stabilization of this carbocation using the lone pair at chlorine. And this accounts for its ability to stabilize the carbocation. Okay? So, we prefer to attack the ortho and para position because the resulting carbocation is stable. In the starting material, there is no carbocation, and the major effect is chlorine's electronegativity. Electronegativity is often referred to as the inductive effect. So we say that chlorine is inductively electron withdrawing, but can stabilize carbocations by resonance, but it doesn't know that it can do that until it actually becomes a carbocation. That's why we see this unusual behavior. Okay, let's look at how do we predict where substituents are going to go in multiply substituted benzene rings. Okay, so there's three general rules. The strongest electron donating group dictates the orientation, and I just refer to this as the boss because it's the only one whose opinion counts. Okay? If there are two or more rings, and we'll see many examples of that, the most activated ring will preferentially undergo the electrophilic aromatic substitution. And finally, if we have two groups that are meta to each other, it's unlikely that the substituents is going to prefer to go here due to steric reasons. However, if this is the only type of position you have, this is where it usually goes. But sterically, this position's disfavored. Okay. The easiest scenario of all is when the groups cooperate. Okay, so we have an electron donating group and an electron withdrawing group in the para position. The electron donating group says put the incoming substituent here, and this is of course the boss. But we have a situation where the electron withdrawing group isn't arguing with this because the electron withdrawing group wants the new group also to go meta to it, which matches ortho para to the methoxy. And we cannot put anything here because something is already here. We don't have a hydrogen that we can replace. Okay, here we have two identical EDGs in the meta orientation. What we find here is that we're not going to prefer to substitute there because it's between two groups, but each of these group guys, or each of these methoxy groups is wanting us to substitute one position or the other, and these two positions here that we're looking at are actually equal by symmetry. Okay, so in the top one, the sulfonic acid that we're going to get is this one, right? Because the new group wants to come in either ortho para to the methoxy, and the COOMe, it's kind of a sycophant type of underling here. It just agrees with the boss. Okay. This is want. Okay, both OMEs want ortho-para direction to the same place, and the predicted product of this Friedel-Crafts acylation is the compound right here. Okay, let's look at some less obvious situations. Okay, here we have three groups, and they're not actually agreeing. If we want to identify the Boss substituent, that's this one, right? This is a strong EDG, a weak EDG, and an EWG. Okay, so we're not going to want to go here because this is between two meta groups. We do want to go there, and the para position to the hydroxy group is blocked. So the predicted product of this reaction, shown here in magenta, is the compound with the nitro group in the ortho position. Here we have two rings. This one at the top is activated because it's got an EDG on it, and this one is deactivated because it has an EWG. Okay, and this sulfonation reaction is expected to put something ortho to that. Para position is blocked, and the alkyl group is usually a stronger electron donor than a benzene ring is. Okay, and this is the expected product. In this case, we have two groups, a strong electron donating group and a moderate electron donating group and a weak electron donating group. Therefore, this one is the Boss substituent. It's going to want to put things here or here. Okay, and this Friedel-Crafts acylation is thus predicted to afford these compounds. Okay, either of these two. There may not be that much selectivity, probably a little bit more of this one here for steric reasons, but there should be a significant amount of both of them. Okay, finally this last one, we have two benzene rings. This one is deactivated, this one is activated. Electron donating group that's moderate, electron donating group that's weak, and also another weak EDG, right? Okay, so this is our Boss substituent, and we're expecting any new group to go here. So the product of this Friedel-Crafts alkylation is expected to be this ethyl methyl benzene derivative shown here. Okay, now we've learned how to predict where they're going to go, and now that we can predict this, now we can plan a multi-step synthesis. As you're doing a multi-step synthesis, the overriding consideration is that you have to get the right orientation of substituents to get full credit for the problem. One of the things that we do with problems in this section is that we give students a privilege that doesn't exist in the real world. Okay? If the ortho-para directors direct to both positions, and as long as your reaction that you choose directs to either ortho-para, you'll get whichever one you need. You're kind of living in fantasy land for now, but as we go on in this class, we'll learn some other reactions that allow us to distinguish from ortho from para. But the key thing here now is to distinguish ortho-para from meta. Okay, another issue is that there's several problems with the Friedel-Crafts reactions. Two of them we've already addressed, sort of, and the last one is a new one. Okay. Issue A here is that the Friedel-Crafts reaction is often accompanied by rearrangements. Issue B, the product in a Friedel-Crafts reaction is usually more activated than the starting material. Thus, there's often a problem with overalkylation. And see, this last problem, reaction doesn't work on anything that's less activated than a halobenzene derivative. And this is true for both the Friedel-Crafts alkylation and the acylation reaction. Problems A and B, however, are not a problem for the Friedel-Crafts acylation. Recall that a resonance-stabilized carbocation is involved in the acylation, so it doesn't rearrange, and the product has a C double bond O on it in the acylation, so it deactivates the ring as it substitutes, and thus you're not likely to over-substitute. Alright, the aromatic COOH group usually arises from the side chain oxidation noted in the previous chapter, where we take like a ethyl or methyl group and burn it away, or turn it into a COOH group with chromium-6, water, and sulfuric acid, or using potassium permanganate. If we have a double bond on a benzene ring, as shown here, this group usually arises from treating the alkyl benzene with NBS and light, followed by the E2 reaction. Okay, so what we'll do now is I'll stop this video and we'll begin the next video with a few synthesis problems.